Hi, I'm Zhi-Yi from National Yangming Jiao University. Today, we are going to introduce our work. Masking improves contrastive self-supervised learning for ConvNets, and Saliency tells you where. Self-supervised learning has excelled in natural language processing with models such as GPT and BERT, employing masked language modeling. This technique involves randomly concealing words in a sentence and predicting the hidden word, significantly enhancing language model capabilities. While direct masking and self-reconstruction on image data haven't yielded significant advances as in natural language processing, the advent of vision transformers marks a breakthrough. Numerous works in computer vision now leverage vision transformer and employ masking and self-reconstruction techniques, collectively referred to as masked image modeling, achieving remarkable success. In self-supervised learning methods for ConvNets, contrastive learning is the dominant method, emphasizing the design of effective positive and negative views for augmentations, integrating more generic augmentations, such as masking and masked image modeling, into the contrastive self-supervised learning framework with ConvNets as the backbone is crucial for enhancing versatility and flexibility. MSCN underscores the problem of parasitic edges when masking is directly applied to image data. This issue introduces trivial features in ConvNets due to the edges between masked and unmasked regions. The constraint arises from regular grid convolutions, limiting the incorporation of positional embeddings and mask tokens, a departure from typical transformer models. The question arises, can masking be seamlessly integrated into the contrastive self-supervised learning framework with ConvNets as its backbone? While previous studies have explored individual aspects of applying masking, our focus is on strategically considering both where and how to implement masking. Here is the overview of our proposed method, which incorporates saliency-guided masking into contrastive self-supervised learning with ConvNets as the backbone. We begin by employing a localization network, FC, to generate a saliency map. This map, built upon SCDA, effectively separates foreground objects from the background in an image. Subsequently, our saliency-guided masking is applied to create positive and hard negative samples, leveraging the saliency information. Finally, these constructed samples undergo the feature encoder to compute the contrastive objective function LNCE. Here we introduce our saliency-guided masking method. We start with standard data augmentation and employ a relaxed constraint SCDA to identify salient and non-salient patches in both the query and key views. We then apply random masking to these patches separately, using the specified masking ratio alpha. Notably, our saliency-guided masking is selectively applied only to the query and the hard negative view, which is a duplicate of the key view with a higher masking ratio. To address the issue of parasitic edges, we propose three masking strategies. First, we adopt the high-pass filtering masking strategy from MSCN. However, the downstream requirement of applying a high-pass filter poses practical limitations. Hence, we introduce a strong blurring strategy, where masked regions undergo significant Gaussian blurring, essentially passing through a low-pass filter. Additionally, we propose the mean filling strategy, where masked regions are filled with the mean pixel value of the input image. These strategies aim to mitigate the challenges posed by parasitic edges. In our approach, we selectively mask only the query branch when forming positive pairs. To explore the impact of masking different branches on performance, we conduct three experiments: masking the key branch only, masking both branches, and masking the query branch only. Results indicate that masking the query branch alone yields the best performance, while masking the key branch alone performs worse than the baseline. These findings align with Huang et al.'s suggestion that maintaining lower variance in a key branch during pre-training can be beneficial rather than the reverse. Our main objective is derived from the info NCE loss. We introduce an extra hard negative sample from the key view, intending to create a distinct separation from the query view. To achieve this, we incorporate the NS loss in the denominator of the InfoMCE loss. In our experiments, we train a feature encoder using ResNet50 as the backbone under MoCo v2 and SceneClear frameworks on ImageNet 100. Subsequently, we conduct downstream classification tasks on 3 datasets, supervisedly training a linear classifier with a frozen feature encoder. The results consistently demonstrate the superior performance of our specific configuration within both the MoCo v2 and SceneClear frameworks when compared to other baselines. In this table, experiments are conducted on VOC and COCO datasets for downstream detection tasks. The COCO also utilized for instance segmentation. In the MoCo backbone, our high-pass filtering consistently yields optimal results. Similarly, within the SceneClear backbone, this setting consistently produces either the best or second-best outcomes. Adios demonstrates a slight performance advantage in this configuration, possibly attributed to their meta design and pre-training tasks aligning more effectively with fine-grained downstream tasks when using SceneClear as the backbone network. Please visit our session to know more details and have discussion with us. Many thanks for your attention.